Now let's talk about the elements that you might see in series. You might have a resistor in series with your load. You might have an inductor in series with your load, or you might have a capacitor in series with your load. In all cases, what you're going to do is calculate the impedance of the element that you have. So for instance, ZR is going to be R, ZL is going to be J omega L, and ZC is going to be 1 over J omega C, or minus J over omega C. And then if you want to find your input impedance, you're going to take ZL and rotate it a distance d, whatever the length of your line is, until you get to a value ZA, and then Zn is going to be equal to ZA plus ZR, or it's going to be ZA plus ZL, and so on. Now let's see what happens when we add parallel lumped elements. Let's suppose that I have a transmission line and I have an inductor here in parallel instead of in series, ZL. Let's suppose that I have the same load I did before, 50 plus J50 on an impedance of 50 ohms. Draw my straight line right out here to the outside. That's my ZL. And then let's rotate our distance 0.1 wavelength, which was right down here the last time. This was my ZA point, and here is our A point right there. Now that's all fine, but at this point I have an impedance, and right here the easiest thing to do is to have an admittance. I would like to have an admittance at ZA, add it to the admittance at ZL, because admittances in parallel add. Well, I know how to get an admittance for ZA. I simply translate it through the center of the Smith chart, like this. Take my magnitude right here, copy it right there. Oops, more like that. This is YA. So from ZA, I can get YA. I can then read the real and the imaginary parts. So I have YA is equal to a real part of about 0.45, an imaginary part. Follow this line. Do not follow the line you drew. Don't follow this one. So the value that comes right out here is about 0.01 J, and I need to denormalize it, which means I'm going to multiply by Y0, and Y0 is 1 divided by Z0, and then I'm going to calculate Y of L, which is minus J over omega L, where L is the inductance, same thing I did before. That value is going to be given in mhos. This value, because I'm multiplying it by Y naught, is going to be given in mhos, and my Y input is going to be YA plus YL, and that value is going to be given in mhos. Now let's talk about the different types of parallel elements that I could have. I could have a resistor in parallel. I could have an inductor in parallel. Or I could have a capacitor in parallel. So here's R, here's L, and here's C. In all cases, I'm going to calculate the admittance. So Y of R is 1 over R. Y of L is minus J over omega L. And Y of C is J omega C. I'm going to do the same thing I did before, which is plot my ZL and rotate the length of the line until I get to point A. And then I am going to convert ZA to YA, make sure that I denormalize. Don't forget that denormalization step, so that I'm now in mhos, and I can say that the input right here is equal to YR in mhos plus YA in mhos. Similarly, Yn is going to be YL plus YA, and Yn is going to be YC plus YA.